We have finally made it to the end of our Six Sigma and Lean Six Sigma Green Belt course, which is based on the Council for Six Sigma Certification's body of knowledge. If you have not done so already, you should download a copy of the Council's Green Belt Training Manual, which covers the 12th through 24th chapters of their complete study guide. The prerequisite White Belt and Yellow Belt training courses cover the first 11 chapters. The training manual can be downloaded from the course description section for this course for free. But before attempting the 120-question Green Belt certification exam, we should take some time to review what you have learned so far in this training course. Because you will only have 3 chances to pass the exam with a score of 70% or greater in order to receive your dual Six Sigma and Lean Six Sigma Green Belt certificates. This review will take about 5.5 hours to complete and has been split into 3 parts, after which you can take the timed exam whenever it is convenient for you. A normal distribution is related to continuous data. This means that your data is associated with random variables that can take the form of any of an infinite number of points along an interval. Temperature over time is a continuous type of data. Yes, you might never see the temperature of a room fall below 40 degrees Fahrenheit, but within a range such as 40 degrees and 80 degrees, there are an infinite number of continuous data points if you measure to a high enough degree of accuracy. Discrete data is not continuous in nature. Discrete data is typically about categorical occurrences. In some cases, discrete data can be converted to continuous data to allow Six Sigma teams to use more statistical analysis tools when working with the information. When that is not possible, however, you cannot use the normal curve or related statistical analysis on discrete data. Discrete data usually involves either binomial distribution or a Poisson distribution. The normal curve, when presented in graphical format or on a histogram, is typically symmetrical in nature. The data elements tend to concentrate along the center of the curve, with the elements fanning out slowly on either side as the curve drops ever towards zero. The normal curve is symmetrical and is the most commonly required for inferential statistics. It can also be described statistically using both the mean and standard deviation. With a normal curve, the curve centers on the mean, and the number of standard deviations away from the mean changes the probability of the amount of data under the curve. The exponential distribution creates a histogram or trend that is exponential in nature. It decreases exponentially as you travel across the x-axis. Exponential distributions are often used when working with data sets that include arrival times, the average or mean time between failures in a process, weight line theories, or distance in time or space between interesting points of occurrence in data, processes, or experiments. At first, the log normal distribution might appear to be an exponential distribution, but on a graphical analysis, it is obviously constrained by zero. The log normal distribution on a histogram is asymmetrical, with the trend line appearing more as a wave that moves across the page. The location and size of the wave varies with each data set. Log normal distributions are often used when working with data sets that describe time durations, such as the time a process or machine is down, or distribution of assets or wealth among the population. Just to make things more confusing, probabilities can fall into families of distributions, such as the Weibull distribution. Data that fits into the Weibull distribution might also fit another distribution. Note that the Weibull distribution relates to continuous data, so the data would not likely fit a discrete data distribution. Weibull distributions can be described many types of data types and are often used when working with reliability applications and failure probabilities that change or vary with time. You will commonly work with normal distributions when applying statistical analysis. Even if the underlying distribution of your data set is not normal, it is still a good idea to be able to recognize common continuous distributions that are not normal. In a graphical representation, the Cauchy distribution often looks like an elongated normal curve with a tighter peak. The logistic distribution also appears to approximate the normal curve and is in fact used in some science and math functions to approximate other symmetrical distributions. This is because the CDF of a logistic distribution is more consistently calculable, and the list goes on. A binomial distribution is used when you are dealing with discrete data and there are only two outcomes for each trial or sample. In short, binomial distributions relate to attribute data. Yes or no, pass or fail, one or the other. A binomial distribution assumes that the outcome of any given trial is independent of the outcome of another trial. If you flip a coin, it will either be heads or tails. If you flip it again, it will only be heads or tails, with a 50% probability for either outcome. It does not matter what happened with the first flip of the coin. In most cases, when considering attribute outcomes, the probability is not distributed evenly between the two elements, as it is with a coin flip. Instead, there is a probability of success as noted by P, and a probability of failure as noted by 1 minus P. For example, if a machine making parts creates defects in 5% of the parts, then you will have two outcomes for each part made. Either the part will be defective or it will not be defective. The Poisson distribution is often used when dealing with data that is distributed randomly within time, distance, or another unit of measurement. For example, the distribution might be relevant when dealing with calls per hour in a call center, traffic accidents per week on a specific block or street, or the number of defects in a batch. In fact, the word per in a metric is a good indication that the Poisson distribution might be useful. The geometric distribution is used when there are two outcomes for a trial. Trials are independent and there is a waiting time before the first occurrence. As with the binomial distribution, the outcome of each trial must be independent. A real-world use of the geometric distribution might include the number of inspections that occur before finding a defective part, or the number of resumes or applications a recruiter reviews before finding the first candidate that meets the minimal job requirements. The negative binomial distribution is also used with attribute data, fail, pass, and other situations where there are only two outcomes for each trial. Many of the statistical analysis you will perform on data will be related to the normal curve, but understanding a few equations related to distributions such as binomial or Poisson helps you to expand your ability to create real-world assumptions about the data. When you can determine the probability for certain events or data points, you can make educated decisions about a process. What is the probability that a cost-heavy event will occur? Is the cost associated with an event enough to create a reason for working to reduce the likelihood of that event? If the probability of a low-cost defect is high, are the total expenses associated with that defect likely to be higher than the total expenses associated with the high-cost defect that has an extremely low probability? These are just some of the questions that teams can use statistics and probability distributions to answer. Hypothesis tests are statistical tools used to draw conclusions based on data. With a basic understanding of the process and process performance, as well as real-time data, or as close to real-time data as possible, Six Sigma teams can draw statistical conclusions that are extremely accurate if they 1. Ensure that the measurement systems are good, 2. Have the right sample size, and 3. Know how to set up the right type of hypothesis test. With a hypothesis test, the measurement system must be accurate or they will skew the results of the test. The sample size must be large enough to draw accurate conclusions about the population. And even with a good measurement system and sample size, a test can still be inaccurate if it is set up incorrectly. Hypothesis tests cover three broad categories. 1. They are used to test whether the data you have fits a particular data model. 2. They are used to compare a statistic to a hypothesis about the data or population. And 3. They are used to answer the question whether something changed within the data, often after a team has modified an input or other part of the process. In the case of most Six Sigma projects, the team probably wants to know whether the process or outcome has improved. While the type of hypothesis test you will use depends on the answers you are seeking and the type of data you have, all of the tests follow essentially the same guidelines. First, you begin with a statistic or criteria that you usually compute from your sample data. Then you create a null hypothesis and an alternative hypothesis, in keeping with the type of test you are dealing with. The null hypothesis is that the two data sets are equal, and it represents that there is no change. The alternative hypothesis indicates that there was a change between the data sets. It can be either not equal to, greater than, or less than. The statistic or criteria is compared against a reference criteria or distribution, and how the calculated statistic compares to the reference criteria determines whether you accept the null hypothesis or reject the null hypothesis in favor of the alternative. Hypothesis tests are a large part of inferential statistics, where we draw conclusions about the overall process or population by analyzing the sample data and measurements. When stating hypothesis, we are not making statements about the sample. We are making statements about the population or entire process. Anytime you draw inferences about a population from sample data, there is at least some likelihood of error. With hypothesis testing, errors come in two types. A type 1 error is when the null hypothesis is rejected when it is actually true. This is also called the producer risk and is measured by the alpha value, a probability between 0 and 1. A type 2 error is when the null hypothesis is accepted when it is actually false. This is also known as the consumer risk and is measured by the beta value, a probability between 0 and 1. In order to determine which hypothesis test to run, you must know which type of data you have, whether it is continuous or discrete. You also need to know the number of levels of interest for the input in question, the distribution of data, whether it is normal or non-normal, what you are testing, whether it is means, median, variance, count, or proportions. Most hypothesis tests deal with one or two levels of interest. We use the one proportion test when there is only one factor for x and only one level of interest for x, the input. We typically have only one set of data, which is the sample and the target. We use the two proportion test when there is only one factor for x, but there is either one or two levels of interest for x, the input. We typically have two sets of data, and you are comparing those two data sets. We use the one sample or pair t-test when we are comparing means. Typically, the t-test is used when working with smaller samples, and the z-test is used when the samples are larger. We use the chi-squared or one variance test when we are comparing the standard deviation or variance between samples. We use the two sample t-test when we are comparing the means between two samples of data for different factors of x. We use the one sample Wilcoxon when we are comparing the medians, not the mean, between a sample and a hypothesized sample, or even when comparing new sample to a sample taken before a change was made. Like the one sample Wilcoxon test, we use the Mann-Whitney test when we are comparing medians. But in this test, we are comparing the medians between samples of two factors of x rather than one. For more complex tests, we may use the analysis of variance or ANOVA, or the design of experiments, the DOE. Why go through the trouble to run statistical tests in order to determine if things are different. Consider this example. An agriculture company growing corn produced an average of 168 bushels of corn per acre each year for 5 years. The company made a change to its seeding process in an attempt to increase the yield of its fields. The harvest following the seed change resulted in an average of 175 bushels of corn per acre each year. Did the seeding change result in a statistically different outcome in yield per acre? The question is the mean corn yield per acre statistically higher following the seed change? Just looking at the numbers presented in this problem, we can see that the mean following the seed change is 175. When you compare that to 168, it is obviously higher. Why would we go through the trouble of setting up and running a hypothesis test? When introducing the normal curve, we noted that it's not always enough to see that a histogram appears to be symmetrical and following the normal curve. Raw data can be deceptive, which is why we ran the chi-squared goodness of fit test in Excel to ensure that the data was normal. The same principle is true when comparing the statistics from the samples. Yes, 175 is higher than 168, but in the case of the corn yield, is it statistically different? Six Sigma teams cannot just answer the question, is this number different? They must answer the question, is this number so statistically different that we can take action on this information? Statistically different doesn't have to do with scale. In one process, the difference between 10 and 23 might not be statistically different. In another process, the difference between 10 and 10.5 might be statistically different. To run a hypothesis test, we typically follow the same series of steps. Step 1, we state the null and alternative hypothesis. The null hypothesis is always written in the form of the perspective that no change or difference occurs or is present. The alternative hypothesis is always written from the perspective that a change or difference is present, either not equals, greater than, or less than. Step 2, we set the confidence level for alpha. Usually, the confidence level is set at 95% for alpha. But other common settings are 99 and 99.9%. A confidence level of 95% means an alpha value of 0.05 or 5%. A confidence interval level of 99% means an alpha value of 0.01 or 1%. And a confidence level of 99.9% means an alpha value of 0.001 or 0.1%. Step 3. We decide which hypothesis test you are going to use. We choose the hypothesis test based on the type of data we have, the statistic we are dealing with, whether mean, variation, or etc., and how many sets of data you have, which are the levels of interest in X. Step 4. Decide whether your sample size is fixed or whether you can select a sample size based on your beta setting. Step 5. Run the test in Minitab or Excel. Step 6. Interpret the p-value against your alpha setting, which tells you whether or not to reject the null hypothesis. And step 7. Translate the statistical analysis into real-world, business-relevant language. Some calculations, such as the chi-squared test, return specific statistics. In the case of the chi-squared test, that statistic is the chi-squared value. These statistics can be valuable in applications and analysis. But for the purpose of hypothesis testing, we are primarily concerned with the p-value. The p-value is returned for each test, and we compare the p-value to the alpha value we set up before we ran the test. If the p-value returned for the test is less than the alpha value you set, then you reject the null hypothesis and accept the alternative. If the p-value returned is more than the alpha value you set, then you fail to reject the null hypothesis and you do reject the alternative hypothesis. Accuracy in inferential statistics requires that you have the right sample size. A retail company with thousands of customers would never make a major product decision based on feedback from 5 people. And Six Sigma teams should never make decisions based on statistical analysis when the sample size is not big enough to create an acceptable margin of error. To understand the importance of sample size, we will first review some important notes about sampling, as it is related to inferential statistics. Six Sigma teams take samples because they want to determine information about a population. With some exceptions, it is very difficult, very expensive, or impossible to run statistical calculations on the entire population of data. However, when we sample the population and draw inferences from those samples about means, proportions, or variances, there is always some risk of error. Some level of uncertainty will always exist when we draw conclusions about a population from sample data. In many cases, a larger sample size helps to reduce the uncertainty of our conclusions. The uncertainty associated with sampling is defined by something called the confidence level, which is also called the margin of error in some applications. You have likely read or seen survey or poll results reported with a margin of error. The fans are 93% in favor of the new team colors, plus or minus 2%. The margin of error in that particular survey was 2% or 0.02. We often set our alpha value at 0.05, which means that we were at least 95% confident in choosing to reject or not reject the null hypothesis. We can make our hypothesis tests even more accurate by defining the power and sample size for our data, particularly when we are pulling the data ourselves and can choose how many samples to take. There are a number of ways to calculate the sample size needed for a particular project, but the most common is to use Minitab. The concept of hypothesis testing errors is key to selecting sample sizes for various hypothesis testing. A type 1 error occurs when you reject the null hypothesis during a hypothesis test when in fact the null hypothesis is true. You might reject the null hypothesis that the mean of the sample is statistically the same as the hypothesized mean, deciding instead that the sample mean is statistically greater than the hypothesized mean. If the sample mean is in fact statistically the same as the hypothesized mean, you have a type 1 error. Type 1 error risks are denoted by alpha. The type 1 error is also called the producer risk. In a manufacturing environment, if the null hypothesis is true but is rejected due to a type 1 error, then material that is within specification, material that is statistically the same as the target, will be rejected. This is a producer risk. It causes waste, extra cost, and lower employee morale. A type 2 error occurs when you accept the null hypothesis when it is in fact not true. If you accept the hypothesis that the sample mean is statistically the same as the hypothesized mean, when in fact the sample mean is statistically greater than the hypothesized mean, then you have a type 2 error. Type 2 errors are denoted by beta. The type 2 error is also called the consumer risk. In a manufacturing environment, if the null hypothesis is false but is accepted anyway due to a type 2 error, then the material that is not within specification, material that is not statistically the same as the target, is accepted. That means products that don't meet this target is passed on to the customer. That is a consumer risk. It could cause returns, unsatisfied customers, poor brand reputation. The appropriate sample size can reduce the risk of either type of error. To perform a sample size calculation, or to have Minitab perform them for you, certain information and assumptions are required. The alpha level is typically set at 0.05 or 5%. The beta level can be set by the experimenter and the sample size calculated from that number. If the sample size is fixed, then the experimenter usually sets alpha and calculates the beta risk from the sample size. The delta level is the practical difference the experiment wants to detect using the test. The standard deviation is the estimated population standard deviation. We need to know whether we are dealing with discrete or continuous data, and we need to know which hypothesis test we will be using. Before you can move on to calculating sample size, some practical considerations must be made with regard to alpha, beta, and delta. In our review of type 1 and type 2 errors, we covered the difference between producer and consumer risks. But that breakdown doesn't work in all organizations or with all hypothesis tests. Because the outcome of your hypothesis tests are going to be used to make real-world decisions, you have to truly understand what the test and its outcomes mean for the business, employee, and consumer. That real-world understanding helps you to set appropriate alpha and beta values. In most cases, you can set the alpha value at 5%. However, in specific experiments, accuracy is extremely important. In medical or drug trials, for example, alpha values could be set to 99% or 99.9%, making it very unlikely that a researcher would accept an alternative hypothesis that a drug caused a change, for example, if it was not correct. The delta or critical difference should always be based on business needs. It is helpful in Minitab to express the delta in terms of sigma or standard deviation. We want to detect the differences of 0.5 sigma or 2 sigma, for example. In general, we set the alpha at 0.05 or 5%. We set the beta at 0.1 or 0.2 or 10 or 20%, which will give you a power of 90 to 80%. And we set the delta with absolute values as required by business needs. In Minitab, we can select multiple delta and beta values to compare which sample size will best fit our needs. Just as there were a number of hypothesis tests to cover a range of data types and questions, there are numerous sample size calculations, all of which can be performed in Minitab. The one sample t-test is for means testing and is used for comparing to a target value, but you must already have a sample statistic about the population. The one sample z is also used for means testing and is used for comparing to the target, but you do not have sample statistics about the population. The standard deviation is also not known. The two-sample t-test sample size calculation is for means testing and is used for comparing means from two sets of data. The two-sample variance test is for variance testing and is used for comparing variance from two sets of data. The one-sample variance test sample size calculation is for variance testing and is used for comparing variance of one data set to a target. The one-sample proportion test sample size calculation is for proportion testing, the rate of x per y, and is used for comparing the rate of one data set to the target. The two-sample proportion test sample size calculation is for proportion testing, the rate of x per y, and is used for comparing two sets of data. The analysis of variance, ANOVA, is for means testing and requires more than two sets of data, but can only be used with one factor for x. The design of experiment, or DOE, is for means testing and requires more than two sets of data and needs more than one factor for x. To understand more about running and analyzing sample size tests in Minitab, we need to walk through the process for most of the tests. You will find the power and sample size calculation tools in Minitab by selecting the Stat menu and choosing Power and Sample Size. Most sample sizes are calculated in the same manner, so we will only cover the one sample Z power and sample size calculation. You will use this calculation in conducting survey sampling for means testing, especially if you don't know the standard deviation for the process or population. This calculation provides you with a jump-off point, a sample size that provides you some relevant information that is as accurate as you define and that you can use as a basis for future sampling. Under the power and sample size from the menu, you can select the one sample Z calculation, which causes a dialog box to pop up. Minitab lets you calculate sample sizes or back into power values if a sample size is fixed, which is why it asks you to fill in only two of the three values. Because we don't yet know much about our data, we leave the sample size blank and provide several parameters for differences and power values. This causes Minitab to provide a number of answers, one for each difference and power value combination, so we can make a more viable decision about the sample size. In this case, we have set the differences or the delta value to zero point 0.5 sigma, 1 sigma, and 2 sigma. We set power values at 0.8 and 0.9 or beta to either 0.2 or 0.1 respectively. Standard deviation for this first pass is assumed to be 1. If we had information about the standard deviation, we could run a more precise calculation or use the one sample t-test calculation. You can include multiple values, so you will be provided with a choice for the best sample sizes. If you click Options, you can change the confidence level or alternative hypothesis to greater or less than a scenario. After we click OK on the power and sample size box, Minitab returns the calculation, which provides you with a comparison of different sample sizes. If you don't have access to other statistical software, many different control charts can still be created in Excel. But because Excel is not designed for creating control charts, it will take many steps and some basic graphical formatting in order to create a full-fledged control chart. That is not something a Six Sigma expert wants to go through every time leadership wants to see an update on a process, and certainly not something day-to-day analysts want to do for regular reporting. Luckily, Minitab offers more automated XBAR control charting. The statistical software also offers easy access to other types of control charting. It should not come as a surprise that there are many different types of control charts, each of which are useful in monitoring different types of data and processes. In order to help you on your way, you will find a lot of pre-made Excel control chart templates in the download section of this course. The X bar and R chart is used when the data is variable and can be grouped into subgroups, letting you chart the mean of each group. You can use it when controlling the production mean per hour, the average answer speed of phones per hour, the average number of customers each day, or the defects per hour. The data count in each subgroup is less than 8, although you can use the X bar and R chart for subgroup sizes up to 100 in Minitab. It is presented using two charts. The X bar control chart plots the mean of each group, and the R chart plots the range. The X bar and S chart is used when the data is variable and can be grouped into subgroups, letting you chart the mean of each group. The data count in each subgroup is more than 8, and sigma can be easily calculated. Otherwise, we use the X bar and R chart. It is presented using two charts. The X bar control chart plots the mean of each subgroup, and the S chart plots the standard deviation. The I and MR chart is used when the data is variable and cannot easily be grouped into reasonable subgroups, so you must track individual data points instead of subgroup means. It is used when the data is very difficult or expensive to obtain. The production is very slow, so waiting for enough data to create subgroups would take too much time, and when the products have a low cycle time. The P chart is used when the data is discrete and is presented as a percentage of defects rather than a count. It does not require a constant sample size or subgroup size and plots the proportion of units that are non-conforming, defective, or do not meet specifications. It is used when it is impossible, very time-consuming, or not financially feasible to measure or analyze numerical measurements when sample or subgroup sizes are not equal. So the percent of defects is more important than the number of defects per group, or when the data is rate-based because it comes from a binomial or attribute process. The measurement or process is pass or fail, go or no go, etc. You cannot plot 1 or 0 on a control chart, but you can plot the percent of 1 or 0 in each sample. The NP chart is used when the data is discrete and is presented as a percentage of defects rather than a count. It does require a constant sample size to be of use. Other than this, you can use it for anything that you would use a P-chart for, and it plots the number of units that are non-conforming in each sample size. The U chart is used when the data is discrete and is presented as a count rather than a percentage of defects. It does not require a constant sample or subgroup size, and it plots the number of defects per unit. It is used when the data is about the defects themselves and not the overall defective product. The C chart is used when the data is discrete and is presented as a count rather than a percentage of defects. It does require a constant sample size or subgroup size, and it plots the number of defects per sample. It is used when the data is about the defects themselves and not the overall defective product. The steps for creating the various control charts in Minitab are very similar, and the main differences between the various charts are the options that can be selected or entered. So we will use the X bar and R chart process using the scenario from the book. A call center is tracking the number of calls on hold. The call center randomly records the number of calls on hold at a given moment 5 times each hour. Once the data is entered into the Minitab spreadsheet, you can select the Stat menu, scroll down to the control charts, and select the variables for subgroup, the X bar and R. This causes a dialog box to pop up where you can enter the information relative to the creation of the control chart. Click into the box under All Observations for a chart are in one column, select your data column, not the interval column, and click on Select. Since the data was sampled 5 times per hour, enter 5 in the subgroup size. Then click X bar and R Options. In the X bar and R Options dialog box, click Test, and in the drop-down menu on the Test tab, select Perform All Tests for Special Causes. This option tells Minitab to perform all the control tests covered by the 8 Nelson rules. If a data point or series of data points on the control chart fails any of these tests, Minitab will highlight them in red, making it easy for Six Sigma experts to tell if a process might be out of control. Click OK on the Options dialog box, click OK on the X bar and R chart dialog box, and Minitab generates a chart and a text description for any failed control test. You will notice that anytime there are failed points, it mentions a test number because these are the 8 Nelson rules that we discussed previously, and a chart can fail multiple tests simultaneously. You can create virtually all of the control charts in Minitab using the same process. The hardest part is interpreting control charts to make valid business decisions or recommendations. Now let us take a break from the numbers and analysis to revisit some fundamental concepts of Six Sigma. When you work extensively with data and analysis, it can be easy to get wrapped up in the numbers without remembering the business needs. In fact, the more you learn about statistical analysis, the easier it is to get caught up in the challenge of the analysis and forget that the business is relying on you for answers about its own challenges. There are a number of obstacles you might run into when communicating your statistical findings to business employees and leaders. And while presenting statistics can be difficult, they still need to be included in presentations, but they need to be included with care. Here is the first and perhaps the biggest challenge faced by Six Sigma experts when delivering information from statistical analysis. Most people don't care. Truly, unless your sponsor is a Six Sigma expert too, or your leadership committee is well versed in Six Sigma methods, the people you are presenting to don't care about which hypothesis test you used or what your chi-squared statistic or p-value was. That isn't to say that business leaders and others don't care about the conclusions or results of your analysis. And they certainly care about the results of the project as a whole. But you have to find a way to present your information in a way that ties in with what they care about and doesn't rely solely on statistical concepts and language. A second challenge is that general business staff and leaders are unlikely to have the same understanding of statistical analysis as a Six Sigma expert does. The Six Sigma presenter is then tasked with presenting data when the backup for that data might not be understood. As a Six Sigma expert, you have to be able to explain why the team chose to move in a certain direction, or how you know a process has improved, and not everyone is simply going to take your word that the p-value was more appropriate for your decision. A third challenge when presenting your analysis is that you can easily become distracted or derailed by the statistics without getting your business point across. This can happen for one or two reasons. First, if your sponsor or another member of your audience is knowledgeable about Six Sigma and statistical analysis, he or she might begin asking statistical questions instead of business questions. Why did you use the one proportion test? How did you choose the sample size? Do you really think a beta of zero point 0.2 is sufficient? Or should you have gone with a beta of zero point 0.1? Some statistical questions might very well be valid. How did you choose the sample size? That might be something relevant to cover in the presentation so that the audience understands what assumptions were made by the team and what risks were considered acceptable. But even with all of those challenges, you should not leave statistics out of your presentation altogether. Whether you are presenting findings at a measure or analyze tollgate review, or you are presenting for final approval on improvements, statistics are what provides your conclusions or results the credibility they need. Incorporating your data into presentations can be difficult, but there are some tips that you can follow to make integrating them easier. It is important to include statistics for credibility, but many people in your business audience are likely not to follow the intricacies of the actual analysis. If you are working in a true Six Sigma environment, then you are never working only with the numbers. When the audience is both invested in the information and capable of understanding many of the statistical concepts behind the decisions made by the Six Sigma team during the project. That doesn't mean you should automatically include all of your data in the presentation. Your audience is also busy. But it does mean that you should anticipate at least a few questions about methodology or statistical analysis, and you can incorporate a few technical terms or results into your presentation without worrying about having to explain them. Use a PowerPoint or another presentation program to combine your information in a way that tells a story that the audience can understand and care about. Keep your audience and the purpose of your presentation in mind. Attempt to tell an overall story across your entire presentation while presenting miniature narratives on each slide. No matter how you are presenting your data, make sure each slide and each element on the slide is clear and concise. Do not misuse PowerPoint. Most audience members do not want to see a 100-slide presentation. Just because you can include it does not mean you should. Don't use Minitab or other statistical analysis software. It takes mere seconds to perform certain tests or create graphs in Minitab. Because of that, Six Sigma analysts and teams tend to accumulate a lot of versions of data. Don't misuse your data analysis skills. Misuse of data analysis can come in two forms. Either you make a data analysis error inadvertently, or you force an analysis to fit a desired outcome or conclusion. Never let the need for a good presentation drive any part of the process. Six Sigma teams should never make decisions about data gathering, graphical analysis, process mapping, brainstorming, or any other Six Sigma function simply because they think it will look good or is easier to present in their presentation.